Hello guys, good evening to all of you. Welcome to our YouTube live session. In this session we'll be talking about the coordinate system. Look, these coordinate systems are very basic thing. You must understand this before you start subjects like electromagnetic theory or mathematical physics. So mainly we talk about this Cartesian, spherical polar and cylindrical polar. On another coordinate system is that is plane polar. So today in this session we'll be talking about all of them, and we'll also try to understand what different expressions of gradient, divergence, called Laplacian in different coordinate system. So this one lecture will be very helpful for you if you are preparing for different competitive exams in physics. Okay, so let me just check about all of them, and we'll also try to understand what different expressions. Okay, so I think everything is all right. So let's move out. Okay, so before we start, if you have not installed our application, you can install it from Play Store. You can also scan this QR code and you can get the application. And guys, before I start, let me tell you that this course has been launched, top 100 most important topics for CSR Net 2024 physical sciences. Here we'll be covering 100 most important topics for your upcoming CSR Net exams, and you can get all the details by visiting this website www.physicshub.in. all the links are given in the description. And other than this, you know, all ISRO scientist or engineer SC test series also there. You know, ISRO examination day has been announced. It will be conducted on 18th of April. So you can purchase this test series if you are appearing for that examination. Okay, so without any further ado, let's start today's discussion. So first of all, what you have to do, what we will do, we'll be talking about the Cartesian first, because unless and until you understand the Cartesian, you will not be able to understand the spherical polar and cylindrical polar. So although all of you know, for the sake of completeness, we will start with Cartesian coordinates. Okay, then we will just generalize the thing. Cartesian coordinate. So when you talk about the Cartesian coordinate, we deal with three variables. We can say x, y and z. This is the first thing. So in Cartesian coordinate, we take these three axes x, y, z. This is like we are doing it from the very beginning. That is why we are also doing these simple things. It may not be simple for all of you, but you need to understand this first before we move on to spherical polar and cylindrical polar. So here we have the three unit vectors x cap, y cap, z cap. Sometimes you also write it in terms of I cap, j cap or k cap. Now if you want to specify any point in a Cartesian coordinate, you know how we do that. We go along x axis. Okay, let's change the color, that will look good. Then you go along the y axis, then we reach to this point. Okay, let's say this point is P, x, y, z. Okay, this is x, this is y, and this is z. So this is a very basic thing you already know. Let's define a vector r. Then for this Cartesian coordinate, how do you define r? R we define it in this way: x cap plus y cap plus z cap. Now it is very easy to understand the length element in this Cartesian coordinate. But before that, what will be the magnitude of this vector r? Root over x square plus y square plus z square. and you also know that the any unit vector along this direction. So, this is the vector r which connects origin to a particular point P, and if you want to find out the unit vector along this direction, then what you do? We do vector r by the modulus of r. This modulus of r is sometimes also written like simple r. Okay. Now, for all the coordinate system, we will try to understand three things. One is line element. How we consider line element? Then we will consider surface element. Then we will consider the volume element. So, in Cartesian it is very easy to understand, like let us say this is one point. Now, if I move along this, then we can define the line element, let us say dl. How do you get dl? dl in Cartesian coordinate we define as dx x cap plus dy y cap plus dz z cap. So, how you can comprehend this? It is like you are moving small amount along x axis, okay, like this, small amount this dy along y axis and small amount along z axis, and you get to the new point. In Cartesian coordinate it is very easy to understand this dl. Okay. Now, try to understand this very carefully. Whenever we will define this surface integral or volume integral, these things will be very important. So, let us consider volume element first, then we will go for surface element. Look, line element and volume element, these two things are easy. Surface integral has some complexity which we will try to understand. So, deta is nothing but the product of dx, dy and dz. Okay. So, line element is done, volume element is done. Now, let us go for the surface element. Surface element, or also we can call area element. First we are covering Cartesian, then we will go for spherical polar and cylindrical polar, and if you guys have any question you can ask me. Okay. I am doing from very scratch so that you understand completely. Now, when you talk about area element, area in mathematical physics you can experience two types of area we generally encounter. One is open surface, another one is closed surface. Open surface and closed surface. What is the difference between an open surface and closed surface? Open surface is that surface which does not include any volume. It may be a simple area like this, a plate. So, this is in 2D, it does not contain any volume, no volume, only area. So, this is an example of open surface, okay, simple plane. Now, what will be the example of a closed surface? Closed surface may be some sphere which contains volume. Okay, this is a sphere, let us say. So, it contains volume. So, for both the cases we will try to define the area element. First of all, let us consider the closed surface, okay, and we will define the area element. One standard rule you will keep in mind here, note, line element, volume element, they do not have any direction, they are scalar thing, but this surface, this is a vector thing, and what is vector will have its magnitude as well as direction. What is the direction of the vector? Always remember, when we will talk about a direction of any surface element, it will be outward drawn normal. Okay, every time follow this and you will not get confused. Okay, so let us take some closed surface, then we will try to understand how we define different surface element. Look, in Cartesian it will be very easy for you to understand, and if you understand it clearly in Cartesian, it will not be a big deal in understanding the in spherical polar and cylindrical polar. So first of all, we need to consider this coordinate system x, y, z. Now what we are considering? We are considering some cube. Okay, so let's consider a cube like this. Let's say the dimension of this cube is a. ये थोड़ा सा अलग हो गया cube, but let's say this is a, this is a, this is a. So it is cutting x, y, z axis at a. Now can you name this? This is the origin. What is this plane? If I am talking about this plane, what is this plane called? This plane is your x is equals to 0 plane. Okay. And what about this plane? What about this plane? What is this plane? This is your y equals to 0 plane. Okay. And what about this plane? This is your z is equals to 0 plane. Okay. Now let's say we want to define some area. And as you remember, I have already told you, area means, direction of area means you have to consider outward drawn normal. So I am considering an area element at this surface. What is this surface? This surface is x is equals to a. Okay. Similarly, if you consider this surface is y equals to a. And if you consider this surface, upper surface, that is your z is equals to a. So I hope you can easily understand this. Now what will be the direction? We have to consider outward drawn normal. So we are drawing outward. So this is your x is equals to a plane. If you go along this infinitesimal change is dy. If you go along this infinitesimal change is dz. So what will be this area? This area will be dA, infinitesimal area. So di into dz. Okay, we have written the magnitude. Now if you want to consider the direction, so direction of dA, you see this is positive x axis, so this is x cap. If you consider a symmetrically opposite infinitesimal area like this, so for this the outward drawn normal will be in the negative x direction, in this direction. Okay, so for this the direction is negative of x. So here the area will be, you see the things are remaining same, and if you consider the vector, it will be minus x cap. Understood? So this is we have defined for closed surface. Similarly, you can define the area element in any of the planes. Okay, so this got a little bit messy, so I am drawing a fresh figure for you, then it will be better to understand. X cap, y cap, z cap. Okay. Now let's say I am showing you an infinitesimal area on this plane. Do identify this plane. This is 0, this is a. So this is your z is equals to a plane, right? So if I draw the outward drawn normal, what will be the direction? This will be the direction z cap. Okay. So, what will be this infinitesimal area? On this we have varying dx, okay, along this dx, along this dy. So, this will be dA is equals to dx dy, and if you give the direction, it will be z cap. And if you consider a symmetrically opposite infinitesimal area here, what will be the outward door normal? Outward door normal will be along this, along the negative z cap direction. So, what will be this area element? This area element will be dA is equals to dx dy minus z cap. Okay. So, one thing you can notice, whatever plane you consider, the direction is coming from that only. Here we have considered x equals to 0 plane, x equals to a plane. You see the unit vector direction is along x cap. If I consider z equals to 0, this plane is z is equals to 0 plane, right? Z equals to 0 plane or z equals to a plane, the unit vector along z cap. Similarly, if you consider an area element here, this, what is this plane? This plane is y is equals to a plane, and what is this plane? This is y is equals to 0 plane. So, your unit vector direction will be along this, and if you consider an infinitesimal area here, the unit vector direction will be along this. This will be along negative y cap direction, and this is along positive y cap direction. So, I hope you have understood. These are all for the closed surface. Okay, closed surface elements. Now, let us quickly tell you about open surface. Okay. For open surface, how do we tackle the area? For open surface, there is no volume. Okay. So, first of all, we need to draw the coordinate system. Okay, in this way. Try to understand very carefully. These are very fundamental thing. Many of you know, many of you do not know, but after this lecture, you will be able to do it easily. I am giving you an area. This is the open area, open surface area. Look, for open surface area, look, for closed surface area, there is no sign in which direction it is traversed, but for open surface area, you must have some sign along which the direction the open surface is traversed. So, let us say we are considering this anti-clockwise. Now, if I consider an infinitesimal area on this open surface, so here what is varying? Dy. Along this direction, what is varying? Dz. So, how can you write the area element here? So, dA will be the product of dy and dz. What about the direction? In which direction it is being acting? Look at this orientation. So, it is like anti-clockwise. So, if you rotate something anti-clockwise, in which direction? It will come to along x direction, right? If something is on yz plane, if you rotate, in which direction it will point? It will point along x direction. So, that is why the direction is x cap. Let us take another area here. But now I am giving another direction like this, 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 this. This is below this xy plane. This is in clockwise direction. Now, if I consider an infinitesimal area here, what is varying along this direction? This is dy. What is varying along this direction? This is dz. And from this, you can see it is pointing in the negative x direction. So, this infinitesimal area, we can write it as dy dz, and the direction will be minus x cap. Okay. So, I hope you understood the concept of closed surface and open surface. Let's now quickly tell you about this gradient, divergence, curl and Laplacian in case of Cartesian coordinates. Okay, first of all, gradient. This whole thing will repeat in case of spherical polar and cylindrical polar. Gradient is defined for a scalar. This is the definition of this is a mathematical expression of gradient. Del del x I cap, del del y j cap, del del z k cap times phi. So this is del phi by del x I cap, del phi by del y j cap, del phi by del z k cap. So as you can see, this is a vector quantity. So gradient of a scalar is a vector quantity. Let's talk about divergence in case of Cartesian coordinates. Divergence is defined for a vector. So let's say V is a vector. So divergence of V is equals to del Vx by del x, del Vy by del y, del Vz by del z. As you can see, this is a scalar quantity. So divergence of a vector is a scalar. Third thing is curl. Curl of some vector, let's say that vector is V. You know it. How we write the unit vectors? I cap, j cap, k cap. Then we write the components of this grad operator, del del x, del del y, del del z. Then we write the components of V, Vx, Vy, Vz. So curl of a vector is also a vector quantity. In Cartesian, things are pretty straightforward. Things get little complicated when we move to spherical polar and cylindrical polar. So these four things will always be useful in your electromagnetic theory and all those things. So grad square phi, this is the grad square, this is called Laplacian. Laplacian of a scalar, grad square phi is defined in this way, and as you can see, this is also a scalar quantity. Okay. So this is pretty much about the Cartesian coordinates. Let's quickly move to the spherical polar coordinate. In spherical polar coordinate, what you use instead of x, y, z, we use here r, theta, phi. So your Cartesian coordinate is like a reference, and with that reference we will define these coordinates. So in spherical polar coordinates, we can define a vector, let's say A. It will have r component ar, and unit vector along r, plus a theta, unit vector along theta, and a phi, unit vector along phi. So it is very easy to understand the unit vector of x cap, y cap, z cap, but what about this unit vector r cap, theta cap and phi cap, in which direction they point? Okay. So, let us consider this coordinate system again. So, in the whole discussion, Cartesian coordinate will be our reference point. This is your x cap, y cap, z cap. So, if you want to define a particular point, let us say P, in a spherical polar coordinate, we have to define with these three coordinates r, theta, phi. What is r? R is the distance from the origin to that particular point. This is the origin, let us say. So, r is this distance. What is the theta? Theta is the angle made by this radius vector with the z axis. Okay. So, this is your theta. What about phi? Phi, to get the direction of phi, you have to take the projection on the xy plane. Okay. And this projection of this radius vector, whatever this projection makes the angle with x axis, that is your phi. So, this is the pretty much thing. Okay. So, you can just quickly write what is r. R is the distance from the origin. What about theta? Theta is the angle made by the radius vector or radial vector, you can say, with z axis. What about phi? Phi is the angle made by the projection vector on, what is this plane? This is xy plane, on xy plane with the x axis. So, we have defined these three variables x, y and z. Now, you can see this r can vary from 0 to infinity. It is measuring from this. So, it can vary indefinitely along this direction. So, the limit of r can go from 0 to infinity. What about theta? Theta can go from, let's say, from along this z axis, theta equals to 0. So, it can vary from 0 to pi. What about phi? Phi, you can see it can show you a round. Okay. So, this is 2 pi in this way, So, phi can vary from 0 to 2 pi. Now, to understand them more efficiently, we need to connect these things with the Cartesian coordinate. So, there exists some relationship with the Cartesian coordinate. Let us say x is equals to r sin theta cos phi, y is equals to r sin theta sin phi, and z is equals to r cos theta. Now, the question is, how do they come? Okay, first of all, let us talk about z is equals to r cos theta. You see, this is r. Okay. Now, let us join this. So, the component along this will be r cos theta. This is pretty straightforward. This is your r cos theta. Okay. Now, this projection, you can imagine it in this way. Okay. So, this whole thing is r cos theta. So, z is equals to r cos theta is understood. And what about this component? This will be r sin theta. So, this thing is falling here. So, this is r sin theta. R sin theta is making an angle phi with x axis. So, what will be this component? Okay, let us draw this one also. if this is r sin theta, this will be your r sin theta cos phi, and you know, if we consider this point to be x y g, so you know this is x, this is y, and this is z, and that is why we get r x is equals to r sin theta cos phi. And if this is r sin theta cos phi, if this is r sin theta, what will be this component? This component will be r sin theta sin phi. That is why we get r sin theta sin phi, and z is equal to r cos theta. This is quite straightforward. Okay, so once these three things are done, what about r? R is equals to, you see, root over x square plus y square plus z square. R is defined. We need to find out theta. What is theta? If you take the ratio from this third relation, you can find out theta. What is theta? Theta is equals to cos inverse z by r. So two variables is are obtained. What is left? Phi is left. How can you find out phi? If you take the ratio x by y or y by x, you will take, then you will get tan phi. So from this we can get phi is equals to tan inverse y by x. So in this way we have defined the three variables r, theta and phi. Now unit vector along r is r cap, unit vector along theta is theta cap, and unit vector along phi is phi cap. What about their direction? So direction of r is very easy to understand. It will be along this direction. This is your r cap direction, and you see theta will be perpendicular to r cap direction, and you can see this is the direction of theta. So the theta direction will be along this direction. Okay. This is your theta cap, and phi cap direction you can see along this phi is changing. So phi cap direction will also be like this. This is your phi cap direction. R, theta, phi, they will be perpendicular. You see, r cap cross theta cap should give you phi cap. You can consider it in this way: r cap, theta cap, phi cap. They are perpendicular to each other. If you take the cross product of r and theta, you get phi cap. If you take the cross product of theta and phi, you get r cap. If you take the cross product of phi and r cap, you get theta cap. And if you reverse the order, you will get a negative sign. Okay. Now, as it was very straightforward in case of Cartesian coordinates, the length element, this is not so straightforward in spherical polar coordinate. So, the length element in spherical polar coordinate we will talk about. Length element is very important. From length element, we can get the idea of surface element and volume element. So, in spherical polar coordinate, length element is given by dl is equals to dr r cap plus r d theta theta cap. You see, along r change is dr, along theta cap change is not simply d theta, it is r d theta, and along phi cap change is not only d phi, it is r sin theta d phi. So this you need to understand. So let me just show you how you understand these things. Okay, so first of all, let's say we defined the vector r. Okay, you have defined vector r like this. Now any change in r is dr. So dr will be like this. This is your dr. Okay, this dr is happening along r cap direction. So this is pretty straightforward. Now what about this r d theta, change along theta? So you see, when you change theta, it is showing change along this. Okay, let me just show you this. Okay, so let's say this is your r and you have given a d theta amount of displacement. So obviously this will again be r. Your change is being carried out along this direction. So this is r, this is r, this is r d theta. Angle is equal to arc by radius. So that is why we get an the change in theta is r d theta. This is the second one. Now how do we apprehend this? Change in phi is r sin theta d phi. So what is happening actually? So let's say this is the scenario. This is r, okay, and let's say this is z axis. So it is making an angle theta with this. Now as I have already told you that what is phi? To get phi we have to take the projection on the xy plane, right? So let's say this is the projection. So what will be this thing? This will be your r sin theta. Now when you changing phi, what you are doing? You are rotating this. So r sin theta is remaining fixed. Only change is happening along, you see, change is happening along this, but r sin theta will remain same, na? Right? So previously let's say r sin theta along this. Now you are giving some change, and r sin theta you are giving some change in r sin theta. So this is also r sin theta. So you are giving change in angle d phi. Okay, so you just add this. So we are drawing this thing above here. So this is what, using the same logic, r sin theta, this is also r sin theta, right? Because you are considering on the same plane, xy plane. So this is nothing but r sin theta d phi. So this is the direction of change of phi, which is r sin theta d phi. So I hope you have understood the change in different direction. This is along r direction, this is along theta direction, and this is along phi direction. Okay, this is the length element, and volume element, this is very small thing. So let's do volume element, then we'll go for the area element. For volume element, what do you do? Volume element is a scalar, you know. D tau. So what you do? You just multiply these things, dr, r d theta, r sin theta d phi. So dr multiplied by r d theta multiplied by r sin theta d phi. So what do you get? You get r square dr sin theta d theta d phi. That is why we write the volume element as r square dr sin theta d theta d phi. Okay, so I hope this is understood. Let's go to the area element now. when we will talk about area element, we will first talk about the closed surface. Okay, closed surface. In a spherical polar coordinate only we deal with only closed surface, so open surface will not come into picture. So let's take the usual example of a sphere. Okay, this is not a circle, this is sphere. Let's say sphere which has radius, let's say r. If you want to define a surface element on the surface of the sphere, how do you define it? Obviously the direction will be along r cap direction. This is pretty straightforward. So remember one thing, the direction will be along the variable which remains unchanged. If you consider this surface of the sphere, what is unchanged? Radius, r variable is unchanged. Whatever point you consider on the surface, r is not changing, radius of the surface is not changing, so direction is r cap. So direction of surface will be along the variable which remains constant or not changed. So if I call this area to be dA, how do you write dA? dA we write, remember this thing, here what is not changing? R is fixed, so this dr will be 0 and other thing will multiply r d theta, r sin theta, d phi. What is r here? R is capital R here. Okay, na? Here your r, it can vary for this whole sphere. If you consider, the limit is not 0 to infinity, it is 0 to capital R. For theta it can vary from 0 to pi, for phi it can vary from 0 to 2 pi. So dr is 0, so r d theta into r sin theta d phi. So small r is capital R here, so r d theta into r sin theta d phi, and the direction is r cap, and that is why we write r square sin theta d theta d phi r cap. And we know that the total surface area of a sphere, what is the total surface area? We know it, 4 pi r square for a radius r. So we can evaluate, this is the infinitesimal area. If you consider the total area, let's say total area, how should you get? Total area, let's say S, total area S will be, if you consider like dA over the whole sphere, okay, whole sphere if you consider, so r is constant, so r square is outside, integration sin theta d theta d phi. So theta is varying from 0 to pi, pi is varying from 0 to 2 pi. So r square, this value is 2, this value is 2 pi, and that's why we write the surface area of a sphere is 4 pi r square. Okay. This is a case of a full sphere. How do we tackle the element if you are given a hemisphere? Let's take the case of a hemisphere. Let's draw a hemisphere first. So it is not looking good. So this is a hemisphere, let's say, and it has the same radius r. Now can you tell me, in this hemisphere, how the variable change? R variable as usual, it can vary from 0 to r. For theta, how it can vary? You see, it's a half sphere, so theta will go from 0 to pi by 2, not pi. But for phi, there is no restriction, so it will be as usual 0 to 2 pi, right? Now, let me ask you a question. If you want to define an area element on this surface, how will you define the area? It is pretty straightforward that you can understand the direction of area is r cap. There is no doubt in that. So, I am calling this area A. So, this is dA. So, what will be the area? What is fixed here? If you consider this curved area, radius is same. Either you consider this surface area here, or you consider the infinitesimal surface area here, or here, or here. At each and every place, radius is same. Small r is fixed. So, dr will be 0. R is fixed means dr is equals to 0. Now, go to the area element. So, dr is not contributing because our change in r is 0. R d theta into r sin theta d phi. But on the surface, curved surface, what is this capital R? Capital R is, sorry, small r is capital R. So, you will write r d theta times r sin theta d phi, right? And what is unchanged here? The variable r is unchanged. So, the direction will be r. So, you can also write it as a note. Direction of area will be along the variable which does not change. So, that is why we write this infinitesimal area to be r square sin theta d theta d phi r cap. Now, if I ask you like what will be the area along here on this surface. So, as usual, you know the direction will be always outward drawn normal. So, the direction will be along this. What is this direction? Okay. So, let us call it dA1 and this is this 2. What will be this dA2? If you consider this plane, what is fixed? R is fixed? No. I am drawing this image outside here. Look, I am drawing only the base outside. This is the thing, okay? Just, and we are considering, let's say, this amount of area. This is the direction. Here, you see, if you consider an element here, r will be something. If you consider an element here, r will be something. So, r is not fixed here, r is variable here. But here, you see, what is fixed? Theta is fixed. At each and every point, what is theta? Theta is pi by 2. So, change in theta will be 0. So, can you tell me what will be dA2? Let us move. dr is changing, so dr will sustain. D theta is fixed, so this second term will not come. So, dr r sin theta d phi, okay, dr r sin theta d phi, dr r sin theta d phi, and as I told you, whatever variable will be fixed. So, here theta is fixed, so the direction will be theta cap. Now, let us do this. Theta is pi by 2, so we can put the value of theta to be pi by 2 here. Okay, sin pi by 2 is 1. Okay, here it is r dn. So r square dr d phi theta cap. Okay. अच्छा यहाँ पे एक ही आर है ना, ठीक है, एक बार चेक कर लो गाइस, आर डी आर डी एफ आई थीटा कैप. So I hope you have understood. Now one example of this volume element we can take up. Let's say I am giving a question. Find the volume of a sphere of radius r. So you know already the expression 4/3 pi r cube. So using spherical polar coordinate, how can you evaluate? So any infinitesimal volume element, if you integrate over the whole volume, you should get the total volume, right? Total volume V. We know the volume element expression is r square dr sin theta d theta d phi. So if you consider a sphere, then you can see there r varies from 0 to, let's say, capital R. If you consider the radius to be capital R, theta 0 to pi, phi 0 to 2 pi, and that is why we get here it is r cube by 3, here it is 2, here it is 2 pi. So that is why we get 4/3 pi r cube. In a very simple straightforward way we can deal with things. So I hope you have understood the surface element in spherical polar coordinate. Let's now talk about the expressions of gradient divergence curl in this coordinate system. Gradient divergence curl and Laplacian in spherical polar coordinate. First of all, let's take a gradient. How the expression change? Gradient of a scalar. So del f upon del r, r cap, plus 1 by r del f upon del theta, theta cap, plus 1 by r sin theta del f upon del phi, phi cap. Divergence. Look, this formula will be very useful while you will study electromagnetic theory. Divergence of, let's say, vector A, 1 by r square del del r, r square ar, plus 1 by r sin theta del del theta sin theta a theta. This ar, a theta, a phi, these are the components of vector A in the spherical polar coordinate, plus 1 by r sin theta del a phi by del phi. This curl expression is little bit hard to remember, but we have to remember curl of A. This is 1 upon r square sin theta. First we write the unit vector r cap. Here not simply theta cap, it is r theta cap. Here it is not simply phi cap, it is r sin theta phi cap, del del r, del del theta, del del phi. Here we write ar, here we have r a theta, here you have r sin theta a phi. So, gradient, divergence, curl, and finally Laplacian. These four things we will do in all the coordinate system. So, Laplacian is denoted by grad square f. So, grad square is the Laplacian, f is a function, 1 by r square del del r square del f by del r plus 1 by r square sin theta del del theta sin theta del f by del theta plus 1 by r square sin square theta del square f by del phi square. So, these are the expressions of gradient, divergence, curl, and Laplacian in spherical polar coordinate. Just note it down. So, from up to this part, the things are pretty trivial. Now, we have to connect this spherical polar coordinate with the Cartesian coordinate. So, our next topic is how to transform the Cartesian coordinates to spherical polar coordinates or vice versa. So, you can give the heading, how to convert how to transform Cartesian coordinates to spherical polar coordinate. This is very important, guys. Questions may come from this. These are basically a fundamental concept which you must learn to solve questions of electromagnetic theory. So, what we have our vector in Cartesian coordinates, let us say ax, x cap, ay, y cap, az, z cap. This is in Cartesian coordinate. Now, we wish to convert it to a vector in spherical polar. In spherical polar, ar, r cap, a theta, theta cap, a phi, phi cap. This is in spherical polar coordinate. But how we can do this? That is the question. You know, when we calculate ax, what you do? Let us say this is a vector a, this is x cap direction. So, to get ax, what you do? Ax is nothing but component of a along x cap direction, means we take the dot product, right? So, this is a pretty much basic concept we have. So, in a similar manner, if I want to calculate ar, what is ar? Ar is like the component of a along r cap direction. So, a dot r cap. What is a theta? A theta is like component of a along theta cap direction. So, you have to take the dot product. A phi is nothing but the component of a along the phi cap direction. So, what we can write? A is this ax x cap and all. So, we can write it as ax x cap dot r cap. So, it is like we have taken the dot product with r cap of this vector. Okay, a y cap dot r cap, a z cap dot r cap. Here also ax we have taken the dot product of A with theta cap. So x cap dot theta cap, ay, y cap dot theta cap, az, z cap dot theta cap. Similarly, it is x cap dot phi cap, ay, y cap dot phi cap, az, z cap dot phi cap. Now the problem is we do not know how to evaluate this thing x cap dot r cap. This thing we do not know. This thing we do not know. This thing we do not know. So for that we are doing a very interesting thing. So let's make a table. A table like this. Our main target is to evaluate these terms. X cap, y cap, z cap we are writing, here we are writing r cap, theta cap, phi cap. First of all, let's write the expressions which we know. X is equals to r sin theta cos phi, y is equals to r sin theta sin phi, z is equals to r cos theta. So whenever you want to calculate the dot product x cap dot r cap, what will be this? It is like taking the derivative of x with respect to r. So this will give you sin theta cos phi. Y cap dot r cap. So similarly, derivative of y with respect to r. So this is sin theta sin phi. Similarly, this z cap dot r cap is cos theta. When you consider x cap dot theta cap, so r derivative we have already taken, so r you have to omit. So derivative of this sin theta cos phi with respect to theta. So this is cos theta cos phi. This is cos theta sin phi, and derivative of cos theta is minus sin theta. Once you have considered r and theta, you have to focus only on phi. So x cap dot phi cap means derivative of cos phi, that is minus sin phi. Y cap dot phi cap, so derivative of phi cos phi. There is nothing left, so this will be 0. So let me just tell you once again what we are doing. So whenever you want to calculate x cap dot r cap, you have to take derivative with respect of x with respect to r. Okay. Once this r is done, you will go for x cap dot theta cap. You have to take derivative of this remaining thing with respect to theta. Once you are done with theta, we will go for phi. So we will take the derivative of the remaining thing with respect to phi, and you get this one. Now you are in a position to tell what is the value of x cap dot r cap. This will be this. This will be your x cap dot r cap. Let's say z cap dot theta cap. Z cap dot theta cap means it will be minus sin theta. Let's say you want to know x cap dot phi cap. X cap dot phi cap is this minus sin phi. So in this way you can find out this. Now the question is, can you express these unit vectors along the Cartesian in terms of the Cartesian unit vectors? What I want to mean, can you express, let's say, r cap, theta cap and phi cap in terms of x cap, y cap, z cap? Yes, we can write. So r cap is nothing but sin theta cos phi x cap. plus sin theta sin phi y cap plus cos theta z cap. Okay, just copying this thing. Okay, so we are now in a position to write r cap. What will be r cap? It will be sin theta cos phi x cap plus sin theta sin phi y cap plus cos theta z cap. Similarly, if you want to write theta cap, it will be cos theta cos phi x cap cos theta sin phi y cap cos phi. We have written it incorrectly, the minus sign will come. Cos theta cos phi, cos theta sin phi, and minus sin theta, minus sin theta z cap. And phi cap is simple, minus sin phi x cap plus cos phi y cap. There is no z component. So in this way we can write the unit vectors in a spherical polar coordinate in terms of the unit vectors in Cartesian coordinate. Okay, let's take a problem like where you can utilize this. Okay, look at this problem. In a spherical polar coordinate r theta phi, the unit vector theta cap at this point. So this is pretty straightforward. In a spherical polar coordinate, we talk in terms of r, theta and phi. Obviously the value of r is 10, value of theta is pi by 4, value of phi is pi by 2. You have to find out theta cap. So if you do not know this technique, you will not be able to do. But if you know that the value of theta cap, we have just written, value of theta cap is cos theta cos phi I cap plus cos theta sin phi j cap minus sin theta k cap. Now the value of theta cap at this point 10 pi by 4 pi by 2 will be, so you have to put theta is equals to pi by 4 and phi is equals to pi by 2 and r is equals to 10. So r is not useful here. So cos pi by 4 cos pi by 2 I cap plus cos pi by 4 sin pi by 2 j cap minus sin pi by 4 k cap. So cos pi by 2 is 0, cos pi by 4 1 by root 2, sin pi by 2 is 1. So 1 by root 2 j cap, sin pi by 4 is 1 by root 2, so minus k cap. So 1 by root 2 j cap minus k cap. So that is given in the option D. So in this way we can easily handle this kind of problems. Good evening, Neha Prasik. So two coordinate system we have completed, Cartesian and spherical polar. Let's go for the cylindrical polar coordinate. After that we will go for plane polar. In one lecture we will be covering all the coordinate systems. Cylindrical polar coordinate system. So if you have understood the spherical polar, cylindrical polar is very easy and it will follow the previous discussion. So here three things will be there. Look, in Cartesian we have x, y, z. In a spherical polar we have r, theta, phi. In cylindrical polar we have r, phi and z. Sometimes people use rho, phi, z also. This z is same of the Cartesian coordinate. Whatever thing z represent in Cartesian, it represents same thing in cylindrical polar. So that is the similarity it has. Okay. So for this also what we have to do, we have to take up the coordinate first. कंटिन्यू क्लासेस नहीं होती है आपकी, हाँ अभी से शुरू कर रहे हैं हम लोग, कंटिन्यू क्लासेस अभी करेंगे, ठीक है. सो दिस इज योर एक्स कैप, y cap, z cap. So if you want to define any point in the cylindrical polar coordinate, say point P, how do you define? You know about the x, y, z thing. Okay. So if you had to define this point in Cartesian coordinate, what you would have done? You will go x distance along x axis. You would go y distance along y axis and z distance along z axis. So this would be your x, this would be your y, this would be your z. What about in cylindrical polar coordinate? So we have to define for r. One difference with spherical polar coordinate, in spherical polar coordinate r is measured from the origin, but in cylindrical polar coordinate r is measured from the z axis. This is the one very fundamental difference. Okay, this will be r, this is not r, not from the origin but from the z axis. Okay, r here, r is the distance from the z axis, not from the origin, and consequently the direction of r will be perpendicular to z axis. So this will be the direction of r, this is your r cap. Now what will be the phi thing? To get phi, we have to take the projection on the xy plane. Okay, so projection of r is on the xy plane like this. So this is r, this will again be r, this is the projection. Whatever the projection making angle with x axis, that will be your phi. So this is your phi. So phi is the angle made by the radius vector or r. Okay, let's write it, made by the projection of r on the xy plane with x axis, and z is z, whatever z you have in your Cartesian coordinate, same z will be there. So what will be the direction of phi? As you can see, phi is changing along this direction. So phi, direction of phi will be along this direction, simple. So this is the phi cap direction, and z cap direction, you say this is the direction of z cap in spherical Cartesian coordinate. So direction of z cap will be like this. Remember one thing, that these unit vectors are perpendicular to each other. In case of spherical polar coordinate also you have seen r cap, theta cap, phi cap, they are perpendicular to each other. X cap, y cap, z cap, they are perpendicular to each other. Here also r cap, phi cap, z cap are perpendicular to each other. Okay. Now we know three relations here. If this is r, what will be this thing? This projection r is making angle phi with x axis, so this will be your r cos phi, and consequently this distance will be r sin phi. That is why in cylindrical polar coordinate we write x is equals to r cos phi and y is equals to r sin phi, and z is z. There is nothing special about z, so z is z. तमाल क्या बोल रहा हो? गुड इवनिंग, काइंडली मेक अ वीडियो ऑन पोस्ट जेस्ट opportunities rank wise. Yeah, we'll try. Nice suggestion. So we are interested in these three coordinates r, phi and z. What is r here? We have to relate r with the Cartesian coordinates. R, from this you can easily see it is nothing but root over x square plus y square. R is defined. Now phi, how can you define phi? You can take the ratio. Phi is equals to r sin phi by r cos phi, so tan phi, so phi is equals to tan inverse y by x, and z is z. So you understood? Now we have to define the line element, surface element and volume element in this coordinate system. And before that, let me give you another idea, like the range of these three variables. What is the range of r? Range of r is as usual, it can go from 0 to infinity. Phi, as usual, you can see that it is ranging from 0 to 2 pi, and z, you see this is origin. Z can vary from 0 to infinity, and in the negative side also it can vary 0 to minus infinity. So this is minus infinity to plus infinity. It has a wider range. Okay. So let's write the line element in cylindrical polar coordinate. So you can give the heading line element in cylindrical polar coordinate. Now when you take a line element, you see you have to consider the change in r coordinate, change in phi coordinate, change in z. Change in r is very straightforward. If this is one point, if you change little bit, it will be along this direction. Change in z is also straightforward along this. But what about the change in phi? So change in r and z is trivial, so we are considering change in phi. So if you change phi, you see an angle is made. Okay. So let's say we have this r and we are making a small change in phi. This is r, this is also r. We are making some change in phi, so d phi change. So change will be like this. This will be the change in phi cap direction. What is this? This is r, this is d phi, this is r d phi. This much is the change in phi. Change in phi is not simply d phi, it is r d phi. Okay. So let's write the line element. To write the line element dl, change in r is dr, no issue, r cap. Change in phi we have just evaluated, r d phi along phi cap direction, and change in z is dz along z cap direction. So if you understand this simple thing, then it will be very easy for you to understand complex things. Book wise है या topic wise? Book wise अभी we are dealing with mathematical physics. Okay. So this is the line element. I hope you have understood line element. Volume element is pretty straightforward. So let's first consider volume element. How to define volume element? Volume element means the product of this thing. So you see dr, r d phi, dz, and that is why we write the infinitesimal volume element in cylindrical polar coordinate to be r dr d phi. Volume element is a scalar, so there is no issue of direction. Now the main headache is the surface element. So how to deal with surface element in cylindrical polar coordinate? Look, needless to say, when we have an object with cylindrical symmetry, we will use cylindrical polar coordinate. We have spherical symmetry, then for those objects we will use spherical coordinate. Like if you have a football, a sphere, then you will use spherical polar coordinate. If you have a cylinder, a pen like this, so for this kind of cases we will consider cylindrical polar coordinate. So obviously for this case we will be considering the cylindrical polar coordinate. So I am giving you a scenario. First of all, let us take a cylinder. सिलेंडर पे लाइन कहाँ से आ गया? Okay, let's make a cylinder. Okay, let's now fix the coordinate system in this cylinder. It is situated, the origin is situated at the middle of the cylinder. Okay, so this is your x cap direction, this is y cap direction, this is your z cap direction, and center of the cylinder is the center, our origin. Okay. Length of the cylinder is, let's say, L. So if you consider this surface, what is this surface called? This surface is z is equals to, let's say, L by 2 surface. Okay, this much is L by 2 and this much is another L by 2, so total is L. What about this surface? This surface is z is equals to minus L by 2. Now I am assuming we want to take an element on the upper surface. So what will be the direction? Outward drawn normal. This will be the direction. If you take an element in the lower surface, what will be the direction of area? Outward drawn normal. Okay. So for this cylindrical case, let's write specifically how r can vary. To define this cylinder, how r can vary? R can go from 0 to capital R. If we consider the radius of this cylinder is R, so R will vary between 0 to capital R. What about phi? Phi can vary as usual 0 to 2 pi. What is Z? Z, you can see it is varying from minus L by 2 to plus L by 2. Now we are interested in writing the surface element. Let's say one surface element we are considering here on the curved surface, and as you can see, what will be the direction of this area element? Obviously it will be like this. This will be the direction of the area element. What is this direction? This is nothing but r cap direction. So if I want to write this, r is equals to capital R. This is how we define this curved surface. So if I write the area element, this is your dA. What will be this value? dr, along the curved surface we have the fixed radius, right? So no change in dr, so dr will be 0. r d phi, so here r is equals to capital R, so r d phi, here dz is dz, and which is the fixed variable here? R is not changing, so the direction will be your r. So this will be your r d phi dz r cap. Understood? Let's say we want to define a surface element on the z is equals to L by 2 plane. Means this, if this is your, let's say, and let's name it dA2 and this is dA1. So this is your dA1. So any surface element on the z equals to L by 2 plane, let's say this will be dA2. What is fixed here? You see, on the z equals to L by 2 plane, z is fixed. So obviously this dz will be 0 and r is not fixed. If you consider an element here, okay, r will be something. If you consider an element here, r will be something. Here r will be something. Here r will be something. So change in r is there. So dr. What about r d phi? Phi is also changing, r d phi. What is fixed here? Z is fixed here. So the direction will be your z cap. So this is r dr d phi z cap. I think now you have understood how to tackle with surface element in spherical polar coordinate and cylindrical polar coordinate. Chalo. Let's quickly talk about the gradient divergence curl in this coordinate system, which is important. Gradient divergence curl and Laplacian in cylindrical polar coordinate. First of all, gradient. So you have to remember these things, okay? Because in electromagnetic theory, when we will be given some cylindrical object, you may have to use this, okay? In applying Gauss law and all, the differential form of Gauss law. What about divergence? Divergence is defined for a vector A 1 by r del r. AR is the component along r direction, A phi is the component along phi direction, and AZ is the component along z direction. What about curl here in this coordinate system? So in spherical polar coordinate we have r 1 by r square sin theta outside. Here it is 1 by r. Okay, r cap, r phi cap, z cap, del r, del phi. Look, these small details are important. It's not like only phi cap, it is r phi cap. Here it is AR, here it is r a phi. These things you have to remember, otherwise you won't be able to solve problems based on this. Okay, I think in magnetization topic, where you will be calculating, I think, surface current, then this formula will be useful. Lastly, Laplacian, grad square, Nabla operator, 1 by r del r, r times del f by del r, 1 by r square del square f by del phi square del square f del z square. So in this way we can write gradient, divergence, curl and Laplacian in cylindrical polar coordinate. Okay, so once it is done, let's now similarly tackle how to convert Cartesian coordinate to cylindrical polar coordinate. Okay, so once you have understood the spherical polar coordinate case, it will be very easy for you to understand the cylindrical polar case. So how to transform Cartesian coordinates to cylindrical polar coordinates. Once we are done with this, we will consider another one, plane polar, then we will wrap up the session. Okay, I will be back in 1 or 2 minutes, just hold on. Okay, let's resume. We have a vector A, let's say, in Cartesian coordinate. It has 3 components, Ax. Let's say previously we have done with x cap, right? So let's follow the same terminology. Ay, y cap, az, z cap. This is in your Cartesian coordinate, and we want to convert it into cylindrical polar coordinate. So in cylindrical polar coordinate will be AR r cap, A phi phi cap, AZ z cap. And as I have already told you, what is AR? AR is nothing but the component of A along r cap direction. Similarly, A phi, component of A along phi cap direction. AZ is nothing but the component of A along z cap direction. So taking the dot product of A with r cap means Ax x cap dot r cap plus Ay y cap dot r cap Az z cap dot r cap. Similarly, write this Ax, okay, x cap dot phi cap Ay y cap dot phi cap Az z cap dot phi cap, and this one finally x cap dot z cap Ay y cap dot z cap Az, okay, z cap dot z cap. Look, z cap is creating no problem, but what about this x dot r cap, x cap dot phi cap? How to calculate this? So to do that, in a similar manner, we are constructing a table. Okay, 3 more lines. This is your x cap, y cap, z cap, r cap, phi cap, z cap. So we will be considering the similar terminology. Here x is equals to r cos phi, y is equals to r sin phi, and z is equals to z. So to calculate x cap dot r cap, you have to take derivative with respect to r. So what is remaining? Cos phi. Y cap dot r cap, sin phi. Z cap dot r cap, there is no related r related term, so this is 0. Once you are done with r, we'll go for phi. So we'll forget r. So x is like cos phi. So derivative with respect to phi is minus sin phi. Derivative with respect to phi is cos phi. Derivative with respect to phi is nothing, 0. For x and z, nothing is there in nothing of z is there in x. So this is 0. Similar for y, 0, and z with respect to z. So this is 1. Okay. So in this way you can write, and in the like we have done in the previous case, here also we can write these unit vectors like r cap, phi cap, z cap in terms of the unit vector of the Cartesian coordinates. So r cap, you can now tell me cos phi x cap plus sin phi y cap. Phi cap will be minus sin phi x cap plus cos phi y cap, and z cap is z cap. Okay, we can write it in this way. One problem I think came in jest based on this. Let's do it. Okay, where is the problem? Okay, look at this problem. The vector field xz I cap plus yj cap in cylindrical polar coordinate is. So you are given a vector in Cartesian coordinate, you have to convert it into cylindrical polar coordinate. E rho cap, E phi cap are the unit vectors along rho cap direction and phi cap. Rho is r here. Okay, E rho cap is nothing but r cap, E phi cap is nothing but your phi cap, and E z cap is nothing but your z cap. So you are now in a position to solve these problems very simply. You can do this problem. So you are given A, which is x z I cap plus y j cap, and you have to find out the same thing in cylindrical polar coordinate. So what is Ax here? Ax is nothing but xz. What is Ay here? Ay is nothing but y, and Az is 0, right? First of all, we need to write this. So E rho cap. Okay, let's first write what will be the form in cylindrical polar coordinate. If you follow the same terminology which is given in the question, so it is like A rho cap. Okay, let's write it E rho cap. Then A phi, E phi cap, Az, Ez cap. Okay, so we need to calculate A rho. What is A rho? A rho is nothing but the component of A along rho direction, right? So this is nothing but Ax x cap dot E rho cap plus Ay y cap dot E rho cap Az z cap dot E rho cap, right? Now you can put the values. What is Ax? Ax is equals to x into z. Okay, so x we have to put in cylindrical polar coordinate. Okay, इसमें यहाँ पे थोड़ा सा हम लोग कर सकते हैं. x into z is equals to rho cos phi times z, and y is equals to rho sin phi, and z is equals to this. Okay, so Ax is equals to rho cos phi into z, x into z, and x cap dot E rho cap. What is this? Okay, हम लोग एक काम करते हैं. Let's copy this thing. This will be useful for us. Paste. Okay. So what we require? We require x cap dot rho cap. So x cap dot r cap. So that is cos phi. So we are putting cos phi. Ay is rho sin phi. Y cap dot rho cap means this sin phi, right? And az is not there, so we don't bother about that. This is rho cos square phi into z plus rho sin square phi. Okay, so a rho is found out. Let's calculate a phi. A phi is a component of a along the phi cap direction. So this is ax x cap dot e phi cap, ay y cap dot e phi cap, az z cap dot e phi cap. So similarly x is rho cos phi times z x cap dot e phi cap. So this is minus sin phi, right? Minus sin phi. Ay rho sin phi and y cap dot e phi cap is cos phi. And az is 0. That is making our calculation easy. So this is nothing but rho cos phi sin phi if I take common, so 1 minus z. So your a becomes rho cos square phi into z. So you can take rho common, na? Sin square phi. This is the component along rho cap direction. And for phi, rho cos phi sin phi 1 minus z e phi cap, and there is no z component, and it is matching with option D, I think. D, or which option it is matching? Z cos square phi plus sin square phi. Rho sin phi cos phi minus z. ऑप्शन ए के साथ मैच करो ना, रो z cos square phi plus sin square phi, rho sin phi cos phi 1 minus z. Yes, option 1. Anyways, so we have covered all those three coordinate system: Cartesian, spherical polar and cylindrical polar. One small coordinate system is left, that we will also cover. Okay, that is plane polar coordinates. Plane polar coordinates. Look, in Cartesian x, y, z, spherical polar r, theta, phi, cylindrical polar rho, phi, z or r, phi, z. In plane polar coordinate, we have two coordinates, r and theta. Okay. So it will be easier for us if we go with our known coordinate system x, y, Cartesian. This is two-dimensional Cartesian coordinates, x cap, y cap. Know this thing, this plane polar coordinate is valid for two-dimensional cases. Okay, so if you want to define any point, you will go along x direction, then you will go along y direction. What about this plane polar coordinate? What is r here? So r, again here it is measured from the origin. This is your r, and this angle is 90 degree between x cap and y cap. So if you want to give the direction of r cap, it is like this. This is the direction of r cap. remember one thing, that theta cap is perpendicular to the r cap direction. So your theta cap will be along this. This is your theta cap, and this angle will be 90 degree. So 2D Cartesian is dealt with two coordinates x and y, and plane polar we have r theta. How they are related? X is equals to r cos theta, y is equals to r sin theta. Straightforward. Okay, let's do one thing. We are drawing this same thing in a single picture. Okay, so we had our x and y. This is x, this is y. Let's not change them. Okay, this is your x cap direction, this is your y cap direction, and you see we can take this thing at the origin. Okay, so this was your r. Okay, so I'm trying to do something. Let's draw a semicircle like this. Obviously this will also be r, and theta is perpendicular to this, so this will be theta. This is your r cap, this will be your theta cap. And as you know, the angle made by r cap with x axis, this angle is theta. Okay, this theta is this angle made by the radius vector with x axis, and the angle between theta and r, you know, this is pi by 2, right? So what is the angle? What is this angle? This angle will be theta plus pi by 2. So theta cap direction is making an angle theta plus pi by 2 with x axis. Okay, so when we want to write, let's say r cap, how do we write r cap in terms of x cap and y cap? You can see r cap is making an angle theta with x axis, so it is cos theta x cap plus r cap is making 90 degree minus theta angle with y cap, so this is sin theta y cap. So in this way we have written the unit vector along r direction in terms of x cap and y cap. How will you write the unit vector along theta cap direction? So theta cap, you can see it making an angle theta plus pi by 2 with x axis. So instead of cos theta, it will be cos theta plus pi by 2 x cap, and sin theta plus pi by 2 y cap. Theta plus pi by 2 means this is in the second quadrant. In second quadrant, cos has negative value. So this is minus sin theta x cap, and in second quadrant sin has positive value. So this is cos theta y cap. So in this way we can write the unit vectors of plane polar coordinates in terms of the unit vector of Cartesian coordinates. Okay. Okay, now let's take an example so that you understand it better. One example I am giving you. Chalo. And after this we will wrap up the session. I am giving you one vector in let's say plane polar coordinate 7 e r cap. E r cap is the unit vector along r cap direction, minus 3 e theta cap. So your ER and E theta cap, these are the unit vectors in plane polar coordinate, let's say. So what is Ax? Ax, we know the component of A along x cap direction, isn't it? So 7 E r cap minus 3 E, अच्छा हम लोग थीटा लिया फाई लिया, थीटा ठीक है, थीटा कैप डॉट एक्स कैप. So 7 ER dot ER cap dot x cap means r cap dot x cap. Okay, r cap you see cos theta x cap plus sin theta y cap. So you are taking with dot product with x cap. So this will give you cos theta, right? So this is 7 cos theta, and r cap means y cap dot x cap, that will be 0. So no term is coming, minus this 3 E theta dot x cap means theta cap dot x cap. So this will come minus sin theta, right? So minus sin theta. This is equals to 7 cos theta plus 3 sin theta. Let's say we want to calculate Ay. So component of A along y cap direction, as usual 7 E r cap minus 3 E theta cap dot y cap. So what will come here? E r cap means this sin theta, we are taking dot product with y cap, so sin theta will come now. So 7 sin theta minus 3 E theta dot y cap, so we have the component cos theta. Okay, so if we give you the value of theta, if theta is given, then we can easily find out Ax and Ay. Okay, so we have today considered 4 coordinate system. Firstly, we have talked about Cartesian, then we went to spherical polar, after the cylindrical polar and the plane polar. So I think after attending this class, your fundamental will be crystal clear, and whatever question you get in your examination, you will be able to handle. So this was a very important lecture. So long lecture, but we have covered everything. So before I end this session, let me tell you guys, you can get such important 100 topics in a single course on this course, top 100 most important topics for CSIR NET 2024. This course has been launched. We'll be covering 100 total most important topics for the upcoming CSIR NET exam. This will be valid for 3 months 10 days, means total 100 days. Okay, whenever you will purchase this, you will be using the benefits for the next 100 days, means 3 months 10 days. And ISRO date, exam date has already been announced. You can also go for the test series. Okay, all the links are given in the description. With this note, let's end this session here. I hope you have understood everything, and if you have any question query, you can let me know in the comment section later on also. Okay, so thank you very much. If you are new to this channel, please subscribe the channel and don't forget to press the bell icon. Good night, see you in the next session. Bye bye, take care.